What if Tesla's newest battery isn't the breakthrough they claim it is? Everyone's hyped about the Cybertruck's 4680 cells, but here's the kicker. Even Elon Musk admits it's not the best tech out there. If it were, why hasn't Tesla rolled it out to the Model 3 or Model Y? Recently, Elon Musk has teased a 5-minute charging sodium battery and a 100 times energy density leap. But what's really going on here? The headlines sound explosive, but the truth behind sodium-ion batteries is way more complex and way more interesting. Can they actually charge in 5 minutes? What's the real science behind that insane 100 times energy density claim? Let's dive into the real story behind the next battery revolution. Welcome to Tesla Car World. Why can this sodium-ion battery be charged in 5 minutes? And what percentage of the battery can be charged in 5 minutes? Energy density, how much juice you get per kilogram of battery, is often seen as the holy grail for electric vehicles and portable gadgets. The higher the energy density, measured in watt-hours per kilogram, the farther you can drive or the longer your device can run without getting bulky or heavy. But when you hear claims of 10 times or even 100 times improvements, it's natural to raise an eyebrow. Are such leaps really possible? Let's start with the benchmark. Today's mainstream lithium-ion batteries, the workhorses in nearly every EV and smartphone, typically deliver around 200 to 300 watt-hour per kilogram. That means for each kilogram of battery pack, you store enough energy to light a 20-watt bulb for 10 to 15 hours. Pushing that to 500 watt-hour per kilogram or beyond could revolutionize everything. But industry projections suggest such gains will play out gradually over the next decade rather than overnight. Now, sodium-ion batteries, long touted for their low cost and abundant raw materials, have historically lagged behind. Early generations hovered around 130 to 160 watt-hour per kilogram, making them more suitable for stationary storage than for long-range EVs. Yet, in April 2025, CATL, the world's largest battery maker, unveiled its Naxtra sodium-ion cells hitting 175 watt-hour per kilogram, narrowing the gap with lithium iron phosphate batteries used in some electric cars today. These cells also boast over 10,000 charge cycles and can operate down to minus 40 degrees Celsius, showing that sodium chemistry is catching up faster than many expected. Even more exciting are the whispers about second-generation designs that could exceed 200 watt-hours per kilogram by the end of 2025. CATL itself hinted that its next-wave sodium-ion packs will break through this 200 watt-hours per kilogram by the end of 2025 barrier, bringing performance closer to LFP and even some nickel-rich lithium chemistries. If realized, that milestone would transform sodium-ion from a niche backup technology into a true contender for everyday EV use. But what about the sky-high claims? 10 times or 100 times energy density. To put it in perspective, a 100 times jump would push sodium-ion into the realm of 15,000 to 20,000 watt-hour per kilogram, rivaling the energy packed in gasoline itself, around 12,000 watt-hour per kilogram. From a chemical standpoint, no current solid-state or liquid electrolyte battery comes close to that. The fundamental limits of electrochemistry simply can't store gasoline-level energy in a safe, rechargeable cell. Even a 10 times increase, boosting a 175 watt-hour per kilogram cell to 1,750 watt-hour per kilogram, remains far beyond today's lab results. That said, focusing purely on peak energy density misses the bigger picture. Real-world performance also depends on factors like cycle life, how many times you can charge and discharge before capacity fades, charging speed, temperature resilience, cost, and safety. A battery that sits at 175 watt-hour per kilogram but lasts 10,000 cycles, charges to 80% in minutes, and tolerates sub-zero winters without fancy thermal management can be far more valuable than a hypothetical 300 watt-hour per kilogram cell that degrades quickly or overheats. In this sense, the recent sodium-ion advancements are already game-changing, even if they don't blow past lithium-ion in a single bound. Where do sodium-ion batteries rank in top EV batteries? When talking about the future of energy storage, it's not just sodium-ion batteries in the ring. Several contenders promise their own game-changing perks. Let's look at 4 of the most talked-about rivals: aluminium, graphene, iron air, BYD's blade battery, and lithium iron phosphate, and see how they stack up. Among the more futuristic contenders is the aluminium graphene ion battery, which combines the lightness of aluminum with the remarkable strength and conductivity of graphene. What makes this battery so promising is its speed. Early lab tests show it can charge in under 10 minutes, all while staying cool. That's thanks to graphene's ability to handle intense currents without heating up, a common problem in traditional batteries. With an energy density ranging from 200 to 300 watt-hour per kilogram, it matches current lithium-ion benchmarks, but the overall battery pack ends up lighter due to aluminum's low weight. Durability is also a highlight, with potential lifespans of over 5,000 cycles. So why aren't we seeing these batteries everywhere yet? The main challenge is scale. Prototype cells exist, but mass production faces hurdles, especially controlling chemical byproducts from the aluminum anode. Still, if those issues are solved, this battery could be ideal for electric vehicles that demand speed and agility. While aluminium graphene is about speed, iron air batteries focus on endurance, offering a completely different advantage. Developed by Form Energy, these batteries are designed for long-duration, stationary storage. Think of them as a backup power source that can keep your home or an entire neighborhood running for over 100 hours. The energy density here is modest, just 50 to 100 watt-hour per kilogram, which makes them unsuitable for EVs. But for stationary uses, that's not a problem. The big win is cost. By using cheap, abundant materials like iron and air, projected costs drop to as low as $20 to $50 per kilowatt-hour, which is dramatically lower than most lithium-ion options. They're also expected to last over 10,000 cycles, since they're not subjected to the physical stresses of driving. Form Energy is already piloting these systems and expects commercial deployment to begin in 2026. For grid storage and renewable energy integration, iron air may soon become a go-to solution. Shifting from labs to real-world impact, BYD's blade battery is already making a name for itself. Built on a familiar chemistry, lithium iron phosphate, this battery uses a unique blade structure that improves energy packing and dramatically boosts safety. While its energy density, around 160 watt-hour per kilogram, isn't record-breaking, it's enough to power EVs for 250 to 300 miles. More importantly, the blade format allows for even heat distribution and reduces the risk of fire, making it one of the safest options on the market. Its performance in nail penetration and thermal runaway tests is impressive. With production in full swing, BYD supplies blade batteries to automakers around the world. It's proof that a smarter design can push even mature chemistries into new territory. Behind many affordable EVs and home battery systems lies the dependable lithium iron phosphate battery. While it doesn't generate as much excitement as newer tech, LFP is incredibly stable, safe, and cost-effective, traits that matter to both consumers and manufacturers. Typical energy density ranges from 120 to 160 watt-hours per kilogram. Its cycle life exceeds 3,000 charges, and it can handle high temperatures and overcharging better than many alternatives. Cost-wise, it remains one of the most affordable choices, hovering around $80 to $100 per kilowatt-hour. LFP continues to serve as the backbone of the EV market in regions like China and is gaining traction in global home storage systems. It may not be flashy, but its dependability is hard to beat. So, which battery is best? The honest answer, it depends on what you need. Need fast charging and low weight? Aluminium graphene could be your future once it matures. Looking for multi-day energy backup at the lowest cost? Iron air might win hands down. Want safe, efficient EV power today? BYD's Blade battery is already delivering, or prefer proven, affordable tech. LFP remains a strong, dependable choice. And don't count out sodium-ion, which is quietly carving its niche with improving density, solid cycle life, and strong low-temperature performance. Especially where cost and environmental impact matter, it's becoming a serious contender. Ultimately, the question isn't which battery is best overall, it's which one best fits your needs today and tomorrow. The battery revolution is unfolding in chapters, and every chemistry has a role to play. Why does liquid metal matter to sodium-ion's future? At first glance, liquid metal batteries, especially ones using sodium-potassium alloy, might seem far removed from the practical world of sodium-ion batteries. But dig a little deeper, and you'll find that the two are part of the same evolving narrative. How to unlock the potential of sodium as a mainstream energy storage solution. Sodium-ion batteries are gaining traction because they're cheaper, more sustainable, and better suited to cold environments than traditional lithium-based cells. Yet their performance, especially in terms of energy density and charge speed, still trails behind top-tier lithium-ion technologies. That's where exotic materials like sodium-potassium alloy start entering the conversation. They might not be ready for mass adoption just yet, but they represent one of the boldest explorations of what sodium can do when pushed to its limits. So what's the connection? With sodium-potassium alloy, liquid nature, and high ionic conductivity, researchers believe it could dramatically reduce this risk while enabling ultra-fast charging. In this way, sodium-potassium alloy-based batteries act like a high-performance next-gen cousin to today's sodium-ion cells. They share a chemical heritage. Sodium is the core of both, but differ in ambition. Where sodium-ion seeks mass affordability and stability, sodium-potassium alloy represents the experimental edge, speed, power, and longevity at a cost of complexity. Of course, sodium-potassium alloy volatility is its biggest hurdle. Unlike solid sodium compounds used in traditional sodium-ion batteries, it is highly reactive. One wrong move, one leak, and it can combust on contact with air or water. That means any practical battery using this must be engineered with extreme containment. Sealed environments, inert gases, advanced materials, and expensive safety systems. This isn't just a technical inconvenience, it's a major cost and scalability issue, especially for EV applications. Ironically, this extreme reactivity helps highlight just how safe and stable conventional sodium-ion batteries already are. In fact, much of sodium-ion's appeal lies in its low fire risk compared to lithium-ion cells, which can enter thermal runaway under stress. Sodium compounds are generally more stable and less flammable, making them an attractive choice for consumer electronics, grid storage, and budget EVs. But these experiments push the boundaries. If researchers can tame this liquid metal, perhaps by pairing it with solid ceramic electrolytes or advanced encapsulation techniques, we could see hybrid sodium batteries that combine the best of both worlds, the affordability and safety of sodium-ion with the performance of cutting-edge materials. So what does this mean for the average driver or homeowner thinking about energy storage? Not much, yet. These designs are still confined to research labs and specialized pilot projects. But the fact that scientists are exploring such extreme forms of sodium-based energy tells us something important. Sodium is no longer a second-tier player. It's becoming the foundation for both mainstream solutions and futuristic breakthroughs. From practical, low-cost sodium-ion batteries powering city buses in China to ultra-high-performance sodium-potassium alloy concepts in experimental labs, the element is proving it can operate across a wide range of needs and formats. In the near term, sodium-ion batteries will lead the charge, literally, especially where cost, safety, and low-temperature resilience matter most. But the ongoing exploration shows that sodium's story isn't standing still. It's evolving fast, and it might one day power both the city bus and the hypercar. What timelines and risk really look like? In the race to electrify everything from cars to homes to power grids, battery innovation is accelerating at a breakneck pace. But here's the hard truth. Just because a battery dazzles in the lab doesn't mean it'll be powering your driveway next year. For every promising prototype, there's a multi-year journey through production hurdles, regulatory hoops, and massive capital requirements. That's why investors, engineers, and energy companies alike are asking, which battery tech is closest to real-world impact, and which still needs time and serious money to grow up? Sodium-ion batteries aren't just the buzzword of the year. They're already beginning to ship. CATL, the world's largest battery maker, announced its Naxtra sodium-ion cell in April 2025. With 175 watt-hour per kilogram energy density, exceptional cold start ability down to -40 degrees Celsius, and cycle lives over 10,000 cycles. This chemistry is aimed squarely at replacing lithium in high-volume applications. Looking to the midterm, 2027 to 2030, iron-air batteries offer a stable, utility-driven growth path. Supported by major grid storage contracts, this technology carries medium risk, but promises steady adoption as more renewable infrastructure comes online. In contrast, solid-state batteries remain a high-risk bet. Though they hold enormous promise in terms of performance and energy density, recurring technical and manufacturing delays continue to cloud their near-future viability. For those thinking long-term, post-2030 and beyond, the focus shifts to speculative technologies like aluminium graphene composites, hybrid solid-state designs, and other experimental formats. These ideas could dramatically reshape the battery landscape, but they are still in early development stages. As such, they're best suited for venture-style investors willing to accept high risk in exchange for the possibility of transformative returns. If you had to bet on just one battery tech for the next 5 years, LFP, sodium-ion solid-state, or iron-air, which would you choose, and why? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. Goodbye.